Alright, so for the first problem of homework 1, we're tasked to find out which one of these two cars has the dead battery firstly. The most important thing to notice is that the current flows from car A, or I should say battery A, to battery B, which means that the voltage of battery A is greater than the voltage of battery B. We know this because conventional current always flows from high to low voltage, and we have a conventional current flowing from car A to car B. So we can say that car B has the dead battery, or battery B, doesn't matter. Car B is dead. So to find out how much energy is transferred to the dead battery, we're given that the time is 1.5 minutes. And we're going to convert it to seconds because for the units to work out nicely, it has to be in seconds because the unit for energy is joules, and it doesn't have minutes in there, it has seconds. So we're going to convert to seconds. So that's going to be 60 times 1.5, which ends up being 90 seconds. So the time we have connected is 90 seconds. The problem gives the voltage is 12 volts, and the current is 40 amps. So anyway, the amount of work done, electrical work done, so we have 0 to t, and then v times I dt. So if we do that quick integration, we have 12 times 40 t and 90 seconds, 0 seconds, because we start at 0. Doesn't matter exactly where you start it, it's just generally you would start at 0, makes it a little bit easier. Anyway, you do the math, 90 times 40 times 12, you get 43.2 kilojoules of energy is transferred to the dead battery. Okay, so for problem 1.13, we have these two boxes. What the boxes are doesn't really matter. We're using them kind of as an arbitrary element that we can assign different values to without making weird assumptions. So anyway, we have 4 cases. We're going to consider the first one. We'll say this is case 1 is A. So case 1, we have 6 amps flowing from A to B, and the potential difference, the voltage across them is 30 volts. So since the current is positive and the voltage is positive, then we're going to get a positive answer. Because the formula to calculate power, there's more than one, but the absolute one that works in pretty much everything. Because there's other ones you need resistance, say like P equals I squared, or there's another one that's V squared over R. But basically, those ones require you to know resistance, and we don't have resistance here, really. And resistance is a complicated topic because it's not always the same. It can vary with temperature, device, frequency, all sorts of stuff like that. So anyway, we're just going to use P equals I times V for now. So 6 amps times 30 volts, we put the unit, equals 180 watts. And we know that it's being delivered because the current is positive and the voltage is positive. So the power in case A is falling from A to B. So case 2 or case B, we have, here's A, and notice we have minus 8 amps. That doesn't mean we have negative energy or negative power or anything. It just means that this arrow right here is actually going in the opposite direction. So we're going to say we have 8 amps going from B to A, or minus 8 amps going from A to B. Either way is the same, it's just your reference. And we have the voltage over here is 20 volts, minus 20 volts. Yeah, minus 20 volts. So anyway, that basically just means we can flip the sign and it'll be the same thing. So if we put the plus over here, then the minus over here, it'd be equivalent. Because remember, the voltages are relative. So if we had like one of these boxes, say this is just, I don't know, a magical box, and we have 21 volts over here and 3 volts over here. If we put, if we used like a voltmeter or a multimeter or anything like that, and we put the positive lead over here and the common or negative lead over here, it's going to see 3 volts minus 21 volts equals minus 18 volts. That's all the minus means, is that it's the opposite direction, sort of. It means that whatever your plus side is 18 volts higher, or 20 volts, or whatever volts higher than the other one. So we call it a minus or a negative voltage. Anyway, so based on that information, we have the current is negative and the voltage is negative. The negatives will cancel out, and we get 20 times 8 equals 160 watts. And since the power is positive, it means that the power is flowing once again from A to B. Case 3, that's not an E. In case 3, we have 4 amps going from A to B, and then a voltage, let's put a plus. So we have V equals 60 volts, or minus 60 volts, minus, okay. So we have the current is positive and the voltage is negative. Once again, we're going to do P equals P times I. So let's put negative 60 volts times 4 amps equals 240 watts, or minus 240 watts. So the power is negative. It means that the circuit inside of box B is delivering power. It's supplying power that box A is dissipating. So that means that the power is going from B to A. Or it's being transferred by the wires, I should say. So anyway, case 4, we have, let's see, case 4, negative 9 amps, so 9 amps going this direction instead of the other direction. Here's our A, here's our B, and we have 40 volts. Okay, so once again, we have the negative current and a positive voltage. So it's going to end up with a negative amount of power being transferred from A to B. Once again, we're going to say it's being supplied by B to A. So anyway, we have 9 times, or -9 times 40, and that ends up being minus 360. And the power is being supplied by B and dissipated by A. For problem 1.29, our task is to find the total power developed in the circuit. So number one thing is we're going to notice is we have a table with all of these currents and voltages. Now to find out the power, it's simple. All we have to do is use basic equation P equals voltage times current. There's a little bit of a trickery going on here, kind of. You got to notice or take note of the direction of the current flow, the little arrow here, relative to the polarity on these voltages. If the current is flowing from, say, let me draw the box again. Say that this is box A, and we have VA right here. There's the plus and the minus. And the current is flowing from minus to plus. There's an IA. Then we're going to have a negative power. So it's going to be VA times IA. Similarly, if we have VB and the current IB is flowing in a direction, the power is going to be positive. So it's just VB times IB. And the significance of plus or minus power is that a positive power means that the component is dissipating that much power, and if it is minus, it is supplying that much power. So when it's asking for total power developed, it's asking for how much power is supplied in this circuit. So we're going to add up all of the negative voltages. And then once we do that, we'll have our answer. Or not, I say negative voltages, negative wattages. So anyway, to start with circuit element A, as we discussed before, we have the current going opposite of the plus. So it's going to be a negative. So power A is going to be negative 18 volts. Oh, let me actually, negative 18 volts times negative 51 milliamps, which will equal negative 0.918 watts. And to do PB, we notice that the current, as discussed before, is flowing from plus to minus, so we are dissipating. So you do that, we have negative 18 times 45 milliamps, and we get an answer of minus 0.81 watts. Now we notice that we still get a negative here, so even though the current was flowing plus to minus, the voltage drop was negative. So that means that we're supplying power still. Because a negative voltage drop just means that from the plus to minus, the plus is lower than the minus. So it's kind of like a voltage gain instead of a voltage drop. If you had it depends on where you put your reference point, because remember, voltages are always relative. So anyway, for component C, we notice that the current is in the same direction as the plus, or it's flowing from plus to minus, I should say, because the positive sign convention. So if we do this calculation, power C is going to be 2 times -6 milliamps. I should do milliamps, just to be not confusing, because it is 1,000th of an amp. So once again, we get a negative answer. This is 12 milliwatts. Let me do that one more time. Power D, we have, notice we have the going opposite of the plus, or from minus to plus, I should say. So we are dissipating. Or not, we're not dissipating, but there's so we have a positive voltage drop, negative current, then we are dissipating. Yeah. So positive voltage drop. Anyway, we have our minus up here because we're flowing from the current is going from negative to positive, or minus to plus instead of plus to minus. And we have 20 volts dropped across it and 20 milliamps flowing through it. Let me actually put the minus here. This ends up being 400 milliwatts. Oops. And this is dissipated once again. For circuit element E, we're going to notice that we have current flowing from minus to plus once again, so we're going to have a minus in front of our equation. But we also have a negative current, so it'll end up being the minuses cancel out. So let's see, minus, and we have 16 volts dropped across it, and 14 milliamps flowing through it. That's an M, not an N. Which will end up being 224 milliwatts. And finally, we have VF, or element F. So we notice going from plus to minus, the current's in this going from plus to minus. So we're going to have a positive over here at the front, so PF, and we have 36 volts times 31 milliamps, and that equals 1.116 watts. So notice our first three elements here. These are all the minuses. So these three minuses means that we are developing or supplying power from those elements, and these elements right here are consuming power. Now if you add these all up, you should get 0, because energy and power is conserved. We can't get anything over unity, and in this model, the only electrical work is heat. So we have a kind of a closed system here, basically. Anyway, so you add up all these three blue ones, you get a total power developed or supplied. You can use either. The power developed will end up being 1.74 watts. For problem 1.31, our task is to check out the power developed and dissipated in the circuit. And we want to make sure that, well, we want to find out if it satisfies the power check. Now the power check is that the power is supplied and the power, oops, let me just do like power supplied. Power supplied and the power dissipated equals 0. As in, we don't have any power that isn't accounted for, or we don't have any, basically, violations of the laws of physics. Or not necessarily violations of laws of physics, but generally in an electrical circuit, energy will be lost as heat. So our task here, much like the previous problem, is to calculate all of these, the power for each circuit element, and we want to figure out if there's sum equals 0 or not. So once again, we start by checking the direction of the current. If the current flows from negative to positive, then our power equation, let me do that a little bit better. Our power equation is going to have a minus up front because it is implicitly supplying power. It may not be. It depends on the voltage drop across it. But based on this table, we have current flowing from plus to minus, but also the voltage drops or increases across it. So it looks like this one's going to end up being supplying. So anyway, we have to also notice we have kilovolts, which is thousands of volts, and milliamps, which is thousandths of amps. So when we have kilovolts and milliamps, if you multiply them straight together, it'll work out because they'll be dividing and multiplying by 1,000. So we could just take the magnitudes of these. We don't have to worry about converting and saying this is 0.25 amps or this is 3,000 volts. So anyway, I'm going to put negative 3 times negative 250, and you should get negative 100 or 750 watts supplied. Once again, we're going to do a similar process for element B. This time, we're going to notice that we have the current is flowing from minus to plus. We're going to have our negative in front. And we have 4 kilovolts and negative 400 milliamps. That's going to end up being 1.6 watts dissipated by that element. PC, or yeah, for PC, once again, minus to plus is the direction of current flow. So we are going to have a negative in front, and we have, what is it, 1,000? Yeah, so 1 kilovolt times 400 milliamps. And we're going to end up with, let's see, yeah, okay. This is milliamps, right? Yes, okay. We're going to end up with minus 400 watts. And for power D, plus to minus is the direction of current flow. So we're going to have a positive up front. And there is a negative 1 and 150. So negative 150 watts. Oh, I'm sorry. It's a plus. Yeah, so 150 watts right there. Power E. We're going to notice we got plus to minus, so we're going to have a plus, or the current's flowing from plus to minus, so we're going to have a positive up front. So negative 4 kilovolts times 200 milliamps is going to equal negative 800 watts. And F, current's flowing from plus to minus. Once again, we're going to have a plus up front. So 4 kilovolts times 50 milliamps equals 200 watts. So we take all of these values, we're going to add them all up, and we'll be able to tell whether or not this circuit satisfies the power check. Ooh, I made a slight mistake. Well, actually not slight. This is 1600. You may have already caught that. But anyway, let's do the math real quickly. So 700 or negative 750 plus 1600 minus 400 plus 150 minus 800 plus 200 equals 0. So the power supplied equals the power delivered, and we satisfy the power check. We don't have any loss or gain that we didn't anticipate, and our circuit satisfies the power check. .32 is kind of like what we were doing before, except working in reverse. So once again, we're tasked with powers and voltages, but we're given power and we're given current. We need to calculate voltage. But the first thing we want to do before we do any of that is we want to show that this interconnection satisfies the power check. So we have a table, and we're given all these values of the power absorbed or supplied by each of these elements. Basically, just have to add all these up together and see if it equals 0. Now, to save a little bit of time, I'm going to tell you right away, these equals 0 when you add them all together. So we know that this satisfies the power check. And to do that, all you have to do is put 175 plus 375 plus 150 minus 320 plus 160 plus 120 minus 660. Promise you that'll equal 0. So the number two thing we need to do is find out which elements absorb power. Now when it says absorb power, it means that it dissipates it or consumes it, converts it to some other form than it was before. Usually that'll be heat, or sometimes a motor, some other kind of form of work. Anyway, you can tell that because it has a positive sign for these. It means that it is not supplying, it is dissipating. So we can say that elements A, B, C, E, and F all absorb power. And our next task is to find the voltage for each of the elements in the interconnection, the voltage drop across them, or the voltage gain. We're going to find the potential difference across them. And we're given the values of power and the values of current, so we can use that equation. And we can, once we have that value, we're going to compare that magnitude of the voltage with respect to the signs across the element. It sounds a little bit confusing, but it's pretty simple like we were doing before. So we'll start with element A. Element A, we have the current is flowing from here. So that means that our power, once again, is going to be plus. And since the power is plus and the current is plus, we're going to get a plus answer. So anyway, voltage A is going to be 175 milliwatts divided by 25 milliamps. And we get that value from this table. We will find that the voltage across element A is 7 volts. Because these millis cancel out, that's 175 divided by 25, and a watt divided by an ampere is a volt. So to find VB, similar process, we're given that the power is plus 375 and the current is 75 milliamps. That's going to end up being 5 volts. 5 volts is the difference across that element. VC, similarly, we have a little bit of a caveat here. Since we have if you go back and look at these, you see how it goes from plus, the current flows from plus to minus here. And in B, current flows from plus to minus. We don't have to worry about flipping a sign there. But in C, the current flows from minus to plus. So we're going to have to put a minus in front of our whole expression. So we have 150 milliwatts divided by minus 50 milliamps. And that is going to equal 3 volts. So the difference across element C is 3 volts. VG, this one we can notice current flows from plus to minus. So we don't have to worry about a minus, we just say there's a plus up front. And we have, what is it? Negative 320 milliwatts divided by 40 milliamps. It's going to equal minus 8 volts. Now once again, minus just means that the voltage, let me use a different color. The voltage over here is 8 volts lower than the voltage over here on the minus side. Because the voltage is always relative, so basically you could flip this around and say that if this was the plus and this is the minus, then it would be 8 volts across. So for element E, we have, what is it? Yeah, okay. So we notice, let me do that one more time. We have the current flowing from minus to plus, minus to plus. So we're going to have a negative sign at the front of our expression. And it's 160 milliwatts divided by 20 milliamps, which is going to be negative 8 volts. And that makes sense because these two elements are in parallel with each other. So the voltage across them is going to be the same. And that's consistent with their answers. Alright, so for VF, we have the current flowing from plus to minus. So we're going to have a plus in the front of our expression. We also have 120 divided by negative 30, so it's going to be minus 4 volts. Pretty straightforward. VG, one more time. Current's going from plus to minus, so we're going to have a plus in front of our expression. And let's see, it's negative 660 divided by 55. This one I can't do in my head, so I'll just do it quickly. minus 12 volts. All right, so if you were to go through this whole thing, you could find out the voltages all throughout the circuit based on this information. So since we have all this information, we have completed the problem, and we can move on to the next one. So for this problem, our objective is to analyze this network and determine if our subordinate that says that this circuit fails the power check is correct or not. And then if they are correct and it fails the power check, we got to see if we can find the mistake that makes the answer wrong. So the first thing we have to do is take a look at our circuit and look at the table we have here. So these are in volts and amps, so they're going to be rather large values for power. And we can start to begin to put this together and figure out what the total power in the circuit is. Now for it to pass the power check, remember, it has to have the power supplied and the power dissipated be equal. That is, like, their sum equals 0. So number one thing we're going to do is start with element A. So PA. And we have, where is it? Yeah. So the current is flowing opposite. It's flowing from minus to plus. So that means we're going to have a negative in the front of this. And we're going to do, let's see, 900 times 22.5. The minuses will cancel out. So 900 times 22.5 is about 20 kilowatts. That's right, watts. PV. We're going to do that same process again. C is a negative, or the current here is flipping negative to positive, so we have minus in front, and it's 105 times 52.5, or negative 52.5. The minuses are going to cancel, so 105 times 52.5. Oops. 52.5. Yeah. Okay, just want to double check my calculation. Yeah, so that's about 5 kilowatts. 5512.5. Power C. We notice we got same deal. Current is flowing from minus to plus, so we're going to have a negative there for the power. Negative 600 times negative 30. So this is going to be a negative answer. 30 times 60, 18, negative 1800, or 18,000, 18 kilowatts. TD. We have, let's see, this one we have the current flowing from plus to minus, so it's going to be a plus in front. I'll do 585, 52.5. And that is negative 30.7 kilowatts. I'm rounding, but yeah, it's just a big number. And PE. This one also is flowing minus to plus, so we have a negative in front, and that means we have, let's see, negative 120 times 30? Yeah. So that's going to be like 4,800, I think. Let's see. 3,600. So it's going to be plus, because the minus is canceled. So 3,600 watts. We're going to do the same process for F. We're going to check, okay, it's flowing plus to the minus, that's going to be plus. You do 300 volts times 60 amps. We get 1,800 watts. And PG, same deal, except this one's going to be start minus. So we're going to do negative, we're going to do 585 times 82.5 times negative 1. It'll be negative 48,262. That's not a 2.5 watts. And power H, flowing minus to plus once again. So we're going to have a negative in front. Negatives are going to cancel, or I ended up with 13,612.5 watts. Now, if we add all of these up together, we're going to notice that we get a total power in the circuit, assuming I didn't make any mistakes, of negative 36,000 watts. So yes, our subordinate is correct. I'll say yes because the power supplied is not equal to power dissipated or consumed or whatever. It doesn't matter. Just we don't have energy conservation basically. So our second task is to, since we've discovered that the subordinate is correct, we've got to try and find the error in the data. Well, if you look at the values for these powers that we've calculated, and we look at the P total, so let me circle that. Our P total is minus 36,000 watts, right? Well, which two of these numbers here look like they would add up or subtract to make 36,000? Well, it seems to me that we have two 1800s or 18,000s here. Maybe one of these has been flipped. So if we look at our data again, and you see that IE is in the reverse direction, right? So IE is reverse direction, that's why we get the minus in front, right here. If we look at the current through there, we get a positive current whenever we're flowing opposite of the convention of the positive side in convention. Does that make sense? No. You can also do a KCL here, because we have this loop here, right? We got this loop here. So if you did the Kirchhoff circuit law analysis for all of these, you'd find out that yeah, there is a discrepancy with IE. We're going to see that IE is actually not flowing from negative to positive. It's actually flowing positive to negative. And when you do that, this sign will flip. And we'll end up getting, oh, I'm sorry, did I say IE? I meant to say IC. So that one's correct, I'm sorry. This one is the one that is flipped. If we did all the analysis and everything here, we're going to find out that instead of a minus, this is going to be a plus because this current is actually going this way. It's not going this way. Because otherwise we'd be violating a law of physics. It has to be that one. So as a result, we found a discrepancy. We can see that this is supposed to be a plus. And the error in the data is that the direction for IC was opposite of what it was supposed to. So this one is the first time that we see one of our common circuit elements. You'll find these in pretty much every electronic device, the resistor. So the important thing to remember with resistors is that they follow a proportional relationship between voltage and current, and that relationship is their resistance. Because the resistance of something can vary due to temperature, it can vary due to frequency, and all sorts of things like that. Those are not topics that, oops, did I do this opposite direction? No, I did the right way. Yeah. So we have instead of this being equal, it's technically more accurate to say they are proportional. That resistance and current and voltage. But we call the famous equation Ohm's law. And it works pretty much all the time. There's very few circumstances where you can't say V equals I times R, and usually those are going to be done by more advanced models than hand analysis like this. Anyway, so our task is to find this current I. Notice that the direction of conventional current through this loop is going to be from positive to negative. And our little I here is flowing opposite of that. So if whatever value that we calculate for this current, this conventional current here through the circuit, it'll be opposite of this in terms of direction, not magnitude or anything. So now that we have V equals I times R, blah, 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 we can find I, the big I, and then use that to find little I. So we can right away, let's just write this so we don't forget, is little I, because it's opposite. So we have our resistance and our current. So to calculate the current, we're going to take the voltage across that resistor, divide it by the resistance, and you will get I. So that is going to lead to 40 volts divided by 2.5 kilo ohms. Remember, kilo is 1,000, so this is 40 divided by 2,500. And 40 volts divided by 2,500 ohms, oops, turn my calculator off, is 16 milliamps, or 0.016 amps. They're the same, just different representations. Anyway, so that's a big I. Remember, big I is opposite of little I in direction. So that means little I is 16 milliamps, or let me put a minus up front, 0.016 amps. We can find the power supplied by the voltage source in a number of ways. We can use our trusty P equals IV. We can also use P equals V squared over R. Or we can use P equals I squared times R. All of these will work, but sometimes one will be easier than another one. And these ones with the R's, you need to know the resistance for you to be able to calculate it. But I'm going to do all three just so we can kind of go over that. Prove that these work together. So P equals I times V. So we're going to do 16 milliamps times 40 volts is 640 milliwatts. That's our what we get when we multiply 0.016 times the V. And it has to be a positive, even though the little I is negative here, because we're trying, well, you can say that it's negative because it's power supplied, but if you want to think in terms of magnitude, it's the same. It's just there's nowhere else for the power to be, and you can't have negative energy. It's just a mathematical convenience whenever we have the minus plus. Anyway, we'll just leave that as 640 watts, milliwatts. Do the same thing here. 40 squared divided by 2500. That's going to be, I think 40 squared is 1600, so divided by 2500. You get 0.64. So 0.64 watts is equal to 640 milliwatts. That makes sense. That is correct. And the last one, we have P equals I squared R. So 16 milliamps squared times 2500 equals 0.64. We end up with the same answer for all three of these, so they're all equally valid. You just generally will use the one that is easier or presents the less challenge to get. So anyway, to do this, if we reverse the polarity, let's say we draw this, let's draw the circuit again. Let's do our ideal voltage source down here. And yeah, I is still the same. So now we have our little resistor, 2.5K and 40 volts. Let me put that outside. Well, now the direction of conventional current is in the same direction as the little I. Little I hasn't changed. We do that same calculation, except we don't have to worry about flipping the sign here. We end up with little I equals 16 milliamps. It's 40 volts divided by 2.5 kilo ohms. And we do the same calculation, we'll find that the power supplied is also 640 milliwatts, or 0.64 watts. Nothing has changed here. The only thing that happened is that we flipped the battery, or whatever voltage source this is around, and it created, or it made the little I go in the same direction as the big I. And there we go. Alright, so 2.13, we have a pair of headlights right here. Let me circle them. Pair of headlights connected to a 12-volt battery, and there is a switch right here that turns them on and off. The triangular symbol right here is the car, it means it's connected to the car's body. So the car is made of metal. You can kind of think of it as a piece of wire, and it connects the the circuit together. Because if you don't have a complete circuit, you won't have any current flow, which means you won't be able to light these lights. So our task here is to construct a model using resistors and an independent voltage source. Well, a resistor, sometimes lights can be modeled as resistors because most of the energy that, most of the power, I should say, that is consumed by a light is lost as heat. Some of it gets turned into light. There's more efficient light sources than others. Say LEDs have more power efficiency than incandescent bulbs, etc., etc. But you can model their power dissipation kind of like that. In the battery, we have an ideal voltage source. In reality, batteries are not ideal. They have internal resistance. They can't deliver unlimited amounts of current. All sorts of complexities that make them not ideal. But for most cases, that it's not as in simple circuits, it's not as big of a deal. Do your best to optimize it and everything. Because you go and buy a battery, you'll see that it has internal resistance in milliohms generally. And that can vary with current, temperature, blah, blah, blah. But we can model as an ideal voltage source for this. You also, I don't know if the problem asked for one, but there is a switch. There's a couple of different representations for switches, but this is one that's pretty common. This one is a single pole, single throw switch, which means it has one arm and one place it can go. And so it has two places it can go, but only one connection. Anyway, we're going to construct a circuit model using resistors and an independent voltage source. We're going to start trying to translating this network, this picture, into a resistor and a switch and battery network. So number one thing we're going to start with is the battery. We're going to say that this is 12 volts. And I don't think they give us a resistance value for these lamps, so we're just going to write it as R. But I want to put the switch into the circuit. Say that we have a normally open switch, and we can close it or whatever. We're going to have two lights wired in parallel. Why are they in parallel? Well, if you look at this connection right here, they share the same sort of top and they share the same bottom. So that means that the voltage across them is the same. So if we have this little network here, connect them all together, they have let's say R1 and R2. So this is R1, R2. And that is our circuit model using resistors and an independent voltage source. I threw a switch in there because there's a switch in the diagram. But it doesn't matter because the lights are on in the picture, so we're assuming the switch is closed. So we can identify the correspondence between the ideal elements and the symbol component represents. Well, like I said before, a battery generally is going to have this very low internal resistance, especially relative to the load that it's driving. So we can model that battery as an ideal voltage source. That's how it corresponds to the circuit element. You can also identify, like I said, the lights themselves can be treated like resistors because they turn pretty much all of the energy that goes through them into heat, like a resistor. There's some light emitted, which is why they're used, but they can be modeled as a resistor. Because inside of these incandescent ones, at least, there's a thin piece of wire usually tungsten. I shouldn't draw it like that because that resembles something you'll see later in this course. But there's a little loop of wire, and that loop of wire gets really high and glows whenever you run a current through it. So that little loop of wire glows because it has enough resistance that it turns. But it doesn't necessarily have enough resistance. It's the amount of current that flows through it is very high. So what little resistance there is going to make it glow. That's how you get things like toasters and ovens and things to heat up, is that electricity flows through them, or current flows through them, and since those things, let's say it's made of nichrome wire. Nichrome is very low resistance. So if you put a lot of voltage across it, you're going to get a lot of current through it. And remember that power dissipated in resistors can be modeled as I squared times R. And you can derive that quickly, because if you have V equals I times R, and you solve for the R and everything, then you end up with a way to write the, because you'll be breaking it up. You'll have I, if we do P equals IV, P equals IV, and we write alternative representations for no voltage, then we can, because V squared over R will be power as well, and R is always to be equals I, blah, blah. But basically, if you model them as lights, those lights as resistors, you'll be able to see that the more current flowing through it will create more and more power dissipated. It won't create power. And that means you can get a lot of power, a lot of heat, a lot of energy radiating from these lights without using too much voltage. You'll be consuming a lot current or consuming power, but you can get a lot of light for not a lot of voltage, which is reasonable. We have a 12-volt battery, which is higher than most modern electronics, but it's a lot lower than your main electricity used in your home. So yeah, that is the correspondence between these circuit elements and the symbols they represent. All right, so for problem 2.14, we're tasked to, we are given this data right here, these currents and these voltages, and we have to figure out a circuit model that would model this device as a single resistor. So we're going to come back to Ohm's law, V equals I times R. And we want to find out what the R is. So to do that, we have to take the voltage and divide it by the current. In the first case, we have negative 10 milliamps divided by, we have negative 120 volts divided by negative 10 milliamps. So that means we're basically going to be multiplying the top by 100, because 10 milliamps is 100th of an amp. But you can do it any way you want. You can say that it's when you divide by a fraction, you multiply it by the reciprocal. Anyway, that's going to end up being 12,000 ohms. For case 2, we have a similar thing, negative 60 by 5 milliamps. Do the math here, you get 12 kilo ohms. Same value as before. just wrote it as kilo instead of thousands, or just regular ohms. We have 60 volts divided by 5 milliamps, 12 kilo ohms. 120 volts divided by 10 milliamps, 12 kilo ohms. I think you can kind of see what's going on here. If you took the 180 volts and divided it by 15 milliamps, you're going to get 12 kilo ohms. So there's a table of values here. We can model the device with a single resistor. Well, notice that all of these are 12 kilo ohms. So we can model our device, say that our device is hooked up at these terminals to our test equipment that we're running these currents from and the voltage. Well, we can put a resistor here and say it is 12 kilo ohms. So if you did the same exercise but in reverse, let's say that we wanted to find out the I here. Let me circle that in a different color. Say we wanted to find the I here. Well, and we put a V of 60 volts. So to find the I, remember V equals I times R. We want to find I, so we're going to do V divided by R, which is going to equal 60 divided by 12,000, or 60 volts divided by 12,000 ohms. We're going to end up with a current of 5 milliamps, or 0.005 amps. They are equivalent. So we have successfully modeled. I hope I didn't cut that off in the video.